Hello, class, and welcome to Review Day. So, as you're working on your case files, you've probably realized, I don't remember how to do some of this stuff because it's been so long. Well, that's normal. You're going to need to use a lot of your friction equations, and then you're going to need to use a lot of your constant acceleration equations, which is what we started the last semester with. So it's been a very long time for some of this stuff. So I have a little review for you. This is in your interactive notebook on page 59, which again should be a page on the right-hand side. All right, draw this. This is called case file kinematics. You got cars. Notice that these arrows are not touching because they are not forces. They're just showing you what direction the cars are going. This is a car that is moving forward with rolling wheels. All right. Here we have a car that is moving forward, but slowing down because you hit the brakes. Another way of saying this is slowing down due to friction. Where here the wheels are moving round and round and round, moving the car forward. Here the wheels are not moving, but the car is still moving forward, leaving these lovely little skid marks on the ground, making that horrible screeching noise. All right. In your case files, a car starts off going like this. Then when it sees something is wrong, it's going to jump right to this. We're not going to do any slowing down, gently applying the brakes. We are going right to slamming on the brakes. The wheels lock and the car skids. All right, which means that when it's like this, you can solve for the acceleration of the car using friction. All right, so if you remember, if this is your car, you have gravity force down, you have a normal force up, you have a friction force going opposite the direction of motion. Again, notice this arrow is not touching the box because it is not a force. Only force arrows touch the box. Other arrows do not. All right, so here we go. Friction. We happen to know the equation for friction is the coefficient times normal force. But we know what normal force is. It's equal and opposite to the gravity force. All right, but we know what gravity is. Gravity is m times g. Okay. So let's just substitute all this back in. That gives me friction force equals mu, the coefficient of friction, times m times g, where that's my coefficient. Here's the mass of the whatever it is sliding to a stop. And this is going to be positive 9.8. Now it's negative 9.8 here. But then look at here. We made it opposite that. So the opposite of negative is positive. Positive. All right. That's important. You're going to want to, highlight that or something, so you remember how important it is. All right, so next you take this and you realize, oh, hey, look, the net force, that's going to equal the friction force here. Because gravity force and normal force, they cancel each other out. Look at this. Equal and opposite on the same object, they cancel out, done. There's only one force on this object, it's friction force. Now notice that friction force is one direction, my velocity is a different direction. This means it's slowing down, which is in fact what we want. So we get m times a. Now, the sign for a must the opposite sign for V, because the car is slowing down. We took an entire page of notes on this idea right here. So if you don't remember that, or you don't understand it, or something like that, you're just not okay with that, you can find it again in your notes. We have done it not too unrecently. Let's see if I can find the page real fast in my notes. And the answer is nope, because I did not keep up my table of contents like I asked you guys to. So hopefully you guys did a better job of keeping your interactive notebook table of contents up better, and you can find it. Oh wait, no, here it is. Sorry, page 2223. That's where you'll find it. All right, this is also important, so I'm going to highlight this. Now, this bit right here is not true always. It's only true for our case files. All right, so friction review, done. We can find friction using all this stuff. Yay. Using friction, I can find the acceleration of my car. Now, once I have an acceleration for my car, well, things get nice and easy. Because now, it's constant acceleration. The very first thing we did together. All right, so let's look at what terms we have. We have VI, which is the initial velocity. This is going to be from before you hit the brakes. You have V final, which is the final velocity. This is, let me say it a different way. This is at the end of the skid marks. So after you've braked, you're done braking, you're at the very end of those lines that get drawn on the ground by the tires, that's when V final happens. Alright, A, that's your acceleration. And remember, you get it from your friction equations. Delta X, that is your displacement. Or how far you've gone, which you are getting from the skid marks. Now, cars don't always make skid marks when they're braking, obviously, but when they slam on their brakes, like you do in an accident, they often do. Alright, and the last thing is time, which is how long you were braking. Alright, so now you take all of this stuff. These things will be given to you in your reports, so the stuff that I gave you. It is your job to take them and your constant acceleration equations and solve for other stuff. Remember, the point of your case files, you need to find the velocity of each car right before they crash, and the velocity of each car right after they crash. Which means that if you have skid marks before the crash, you're solving for V final. But if you have skid marks from after the crash, what you're solving for is V initial. Alright. That's important. So let's have a mini example problem now. I know you're very, very close to the very end of your page. You should have just enough to squeeze this in at the bottom. Example. A 1,200 kilogram car is driving positive 11 meters per second. It then hits the brakes and skids into a brick wall. The tire marks are positive 5 meters long. If the coefficient of friction between the tires and the road is 0.4, how fast was the car going as it hit the wall? Alright, so, if you remember how I like to do word problems, I read it once. I read it twice and I underline all the numbers. Alright, there's that, that's mass. There's that, and then it hits the brakes, so this is the initial. Tire marks are 0.5 meters long. Coefficient of friction is that. How fast is what I'm solving for. Alright, let's make a little list of things we know. We know that m is 1200 kilograms. We know that vi equals positive 11 meters per second. That delta x equals positive 5 meters. Ugh, my handwriting's getting gross. Let's see. We also know the coefficient of friction is 0.4. No units on that. Alright, well, if I look at my notes, I realize that I can figure this out, because I know the friction force. The friction force is going to be mu times m times g. The friction force is going to be 0.4 times 1200 times positive, remember why, 9.8. The friction force is, let's see, 0.4 times 1200 times 9.8 equals 4,704 newtons. Alright, I know that my net force equals mass times acceleration. I know my net force is equal to my friction force. So 4,704 equals 1200 times A. Which means the acceleration of my car as it is getting to a stop is going to be 4,704 divided by 1200. Alright, so let's do that. And I get 3.92 meters per second per second. But wait. In my notes, it says my acceleration has to have the opposite sign as the initial velocity. My initial velocity is positive, so my acceleration must be negative, which means I need to write it in. Okay, so now let's look at what we know. We know v initial, we know delta x, and we know a, and I want to know v final. Well, what equation is that? Alright, well, let's look at our equation list. I want something with v initial, v final, acceleration, and displacement. Let's see. I found it. There is only one equation that has all of those things in it. And it is v final squared equals v initial squared plus 2a delta x. I'm going to plug in my numbers now. V final squared equals, let's see, 11 squared plus 2 times negative 3.92 times positive 5. Alright. V final squared equals 11 times 11 is 121. 2 times negative 3.92 times positive 5 equals negative 39.2. Means v final squared equals positive 81.8, which means that v final is the square root of that. Square root of 81.8 equals 9.04 meters per second. But I'm not done, I need a sign. Is my velocity positive or negative? Well, I was going in the positive direction. Then I hit the brakes, so I'm still going in the positive direction. I have not stopped and turned around. Since I have not stopped and turned around, I am still going forward. Alright, there we go. Answer. Now, in your case file, this would just be a small piece of the overall problem. You have now figured out the velocity of the car right before the crash, for instance. So now you can plug it into your conservation of momentum equations to solve for the velocity of the cars right before the crash. Plug that into the friction equations again to find the velocity of the car before it hit the brakes, well before it crashed. Sounds confusing? That's because it is. And it's why pictures are so incredibly helpful. Even if you just do it with, blobs. Here's car A. Here's car B. Oh no, car A sees car B. So car A is now skidding to a stop. They crash. Car B goes rocketing off. And car A goes rocketing off. Now that I have this picture drawn, what I just solved for is starting here, going here. If you draw a picture, it really, really, really helps. All right, with that, I have a worksheet that I want you to do, just a few more simple example problems like this. Then I want you to spend the rest of class working on your case files. You guys have a lot of work to do still, and when I get back, which is going to be the 3rd of February, not tomorrow, but the Tuesday after, I expect those case files to be done. The reports don't have to be finished, but the math should be. If it isn't, I'll be there to help. Go.